A new coding harness has been added into the agent fleet. It's called Prime Agent. But we already have Claude Code, Codex, Cursor, and Pi, and a dozen other harnesses. So, what is the need for another one? So, Prime Agent has one interesting architectural claim. Instead of giving the model collection of separate tools and repeatedly pushing every tool result back into the model context, it gives models a Python control environment. The model can use that environment to inspect files, run shell commands, and launch subagents. It is built mainly around two ideas: recursive language model for managing long running contexts, and continual harness for letting the agent update parts of its own memory, skills, and prompts. But before that, let's understand how the baseline harness works. So let's say I open Codex or Claude Code and say something like build an authentication feature inside this repo. Now the request is routed to the harness. Harness adds the current working context into the request. Then it goes to the model. Model decides if it needs more information. Then it makes tool calls. The tool response again becomes the part of the model's working context. The model reasons again, can make more tool calls, and this loop repeats until a stop condition is met. This works extremely well. And the bottleneck is not that the agent can't build responses, read files, or run tests. Those things are already solved. The problem appears when the task becomes very large or very long. So let's say instead of building an auth feature, I say something like research the market. Then according to that research, build and complete SaaS feature and run the benchmark. Now the agent may have to read hundreds of files, produce thousands of lines of shell output, try several approaches, make decisions, and receive results from multiple subagents. And at some point, the harness cannot keep putting everything into the active context, so it starts compacting the older context, and here the problem appears. So, how do we keep a large amount of useful working data available without continuously stuffing all of it into the model context? That is the first problem Prime Agent is trying to solve. Now, the obvious question is, if frontier models can have 1 million contexts and newer models are moving towards multi million token context, so why do we need to worry about this? A bigger context can solve this issue, right? Well, no, the bigger context can mainly help solve capacity, not the relevance of data. So, inside the context, we have three separate problems. First one being capacity. Can the information fit into the context window? Second one being cost. Do we need to keep carrying that much context through a long session even with prompt caching? Third one being relevance. Does the model actually need all of that information for the current reasoning step? Now, prompt caching makes repeated prefixes much cheaper, but cheaper is not same as free. A massive long running session can still become expensive, and more importantly, most of the old information may not be useful for the next step. So, a 1 million or 10 million context window and prime agents are not really competitors, they live at different layers. Now, you might ask, haven't we solved a lot of this already? Like, we already have long running goals and markdown memory, right? Codex, Claude Code, Cursor, and other agents can already run long tasks. We can maintain separate markdown files for planning, progress, decisions, and overall memory dump. And we can tell the agent to update them after important steps. And yeah, this is already a very good solution. So suppose the agent finishes a long debugging session and writes something like auth bug probably caused by refresh token validation. Check middleware next into the markdown file. Now, this information sits outside the conversation context. Even if the session is compacted or a fresh agent starts tomorrow, it can read the markdown file and reconstruct the important state again. So, persistent memory is absolutely not prime agent's invention, but the limitation is that markdown normally stores the summary of the state, not necessarily the entire useful structure behind it. So imagine the agent actually found 40 relevant files, 3000 log lines, 18 test outputs, and was running 4 parallel subagents. But what does it write into the Markdown? Auth bug probably caused by refresh token validation, check middleware next. Nothing is wrong with this, but notice what happened. We converted agent useful structured data into a human useful prose. While on the other hand, Prime tries to store every piece of working state by default. There is no need to maintain markdown files or keep prompting the agent to update the changelog again and again. So during a session, Prime can store things in Python variables inside a persistent IPython kernel and query those values later. So when the main LLM context gets compacted, the Python working state can still remain available. Now, what exactly live inside Prime's Python environment? The Python environment is not another copy of the whole conversation. It is a working namespace. So it can hold Python variables, import modules, helper functions the agent created, file list and transform data, RLM API used to create subagents, uh, and host bridge APIs such as goals, messaging, and refinement. And these variables can survive across context compaction because the IPython kernel is different process from LLM context. Also here the model itself is effectively using Python kernel as a control plane environment and deciding what to inspect. So let's say if the agent accumulated 3000 test results, it keep all those results outside the model. Python then filters out only failed auth results, and after the filtering it may find 12 useful rows that goes back into the model context. Then model reasons over those 12. So Prime is not trying to prevent information from ever entering the context. The model still needs information in the context to reason with. It is just trying to control how much comes back at each step. So now with that, we have covered how Prime is able to handle long running tasks. Let's talk about continual harness as well. So continual harness performs selected durable learnings that should improve future behavior of your agent, such as memory, reusable skill, prompt note, or sub-agent specification. So for example, if the agent has 18 test outputs, they don't mean anything. But over a few sessions, the agent may learn that every integration test in this repo must start Redis before migration. So that smaller reusable lesson later becomes a part of the memory. Also, this self-improving agent concept may sound familiar to you, as Prime did not discover the idea that an agent should learn from the previous work. The closest existing tool that is working on the same concept is Hermes. Hermes already has a persistent memory, reusable skills, long running goals, and an actual self improvement loop. So let's try to compare both. So, Hermes broadly separates reusable knowledge into memory and skills. Memory is small factual knowledge, environment details, or useful facts. Skills are procedural knowledge, so they are how to do recursive tasks without being stuck. So, for example, Hermes handles your request, a background review examines what happened, and try to answer, did we learn something reusable? If yes, memory or skill is created or updated. That durable knowledge is available in future sessions. Now, Prime works on a similar idea but formalizes a slightly broader harness state. So, rather than only storing general agentic learning, Prime store prompt nodes, memory, skills, and subagent definitions. During runtime, this state is exposed programmatically through RLM harness, and every change is also written to disk. So the difference here is mainly architectural and the use case each tool is focused on. Where Hermes focuses heavily on persistent, personal, and general agentic learning, Prime focuses more heavily on programmable context and agent orchestration and also harness refinement. Also, Hermes is more automatic and continuous. After enough activity, a separate background review agent can inspect what just happened and decide whether something should be written into the memory or converted into a skill. That means the main agent can finish a task and the learning pass can happen in the background. While Prime makes the refinement a first class harness operation, You could manually run it using /refine command, or the agent can call it internally as well. The base system prompt remains immutable. /refine only edits the harness layer around it, and the refinement keeps before after history, so a bad update can be rolled back. Now let's run Prime locally and see how it works internally. So to install Prime locally, you can run this command in your terminal. Install Prime agent globally with npm. Yes. Prepare IPython runtime now. So this is the IPython kernel we are talking about. Okay, so Prime agent is installed on our local machine. Let's log in. Let's continue with Google. Authentication successful. Now we'll be choosing a provider. I'll go with GPT 5.5 OpenAI Codex. Authentication successful. And we have successfully installed and set up Prime on our machine. Now to start with, we'll create a small Node.js task tracking app. Paste the prompt here. Okay, so Prime agent has created the local demo app. And apart from that, it has also set up two local artifact directories in our local machine as well. The first one is .ipython and the second one is .prime. So let's break them down as well. Now, if we see inside iPrime directory, we have our session files and session artifact files. But we discussed that Prime stores everything in its IPython kernel. So what is this? So think of Prime as three level of state. LLM context, this is what the model is actively reasoning over. Then the IPython kernel, it handles Prime runtime state. And then the TypeScript host, this is what lets the runtime recover and resume after process failure or detachment. This is what we just saw. The actual agent and sub-agent lifecycle, provider calls, and usage are handled by the TypeScript host. The IPython kernel is the model-facing programmable environment. It does not directly implement the model provider loop. When Python needs an authoritative operation like spawning an agent or changing a goal, it sends a typed request back into the TypeScript host. Why? Well, because what happens if Prime crashes or any of the worker crashes in between tasks? We have a recovery session file. That is why this TypeScript host folder exists locally. Still, everything in runtime happens in the IPython kernel. It is just to handle the recovery state. Apart from that, it stores auth.json, which will contain your provider's secret key, logs, which will actively store the session logs created by your worker and parent agent. Session artifacts will store the supporting runtime session state. On the other hand, the IPython directory contains mostly the standard IPython machinery. History.sqlite is the IPython's command history. We have separate DB, log, and other startup and runtime directories. In the harness, we can also see the /refine command that we discussed earlier, which is used to run the self-improving pipeline in Prime. We can trigger it manually, or the agent can also run it in the background automatically. Now, coming back to our demo, we'll create a analytic summary feature and spawn a analytic specialist subagent. So now we can see here our parent agent created a sub-agent using RLM APIs. So where other harnesses create new sub-agents for every task, Prime states that it can create persistent sub-agents. So now what we will do, we'll again spawn the same analytics specialist sub-agent to work on a new analytics feature. So now we can see here the same analytics specialist subagent was reused for the new task. So instead of every delegated task eventually collapsing back into the main agent's context or summary file, Prime can keep a specialist as a persistent addressable session, inspect it, resume it later, and preserve that worker across parent compaction. Now what we will do, we will run these queries inside Prime one by one. So we can clearly see inside the list of subagents, we have an analytics specialist which completed its task, and then it showed us the metadata for that session as well. So similarly, our LLM provider is able to query the IPython kernel to fetch the relevant data that is required in the context. Now, can a normal harness like Codex or Claude Code with structured Markdown reproduce most of this? For normal software work, honestly, yes, a surprising amount of it. And we can tell it store experiment results in your SQLite, keep only conclusions in Markdown, query the DB instead of reading all logs. At that point, we have reproduced a large part of Prime's external state idea manually. So the fair comparison is Prime makes external programmable state the default harness architecture instead of something we have to design ourselves through prompts and files. So for a 15 file Node.js project, that extra machinery may give almost no practical advantage. But for a long autonomous evaluation that generates hundreds of experiments, several independent agents, and millions of tokens of observation, the difference becomes much more interesting. Now, you might ask that at what task size does RLM actually beat normal compaction? There is no verified repo size threshold like after 100 files, Prime becomes better. That would be fake precision. The better trigger is not the number of files, it is the amount of useful state that must remain queryable while the task continues. So RLM starts making more sense when several tasks repeatedly produce large tool output. Earlier raw results matter again much later. The main session is compacting multiple times. Several independent investigations can run in parallel. The agent needs to compare many experiments rather than just remember one conclusion. The job runs for hours rather than few focus turns. Now, a sensible person might ask what extra token and compute cost does Prime add? Prime can save parent context tokens, but subagents are not free. Every child created with RLM is another actual agent session with its own model calls, its own context, its own tool use, its own reasoning and output tokens. So there are two forces working against each other. The first one being savings. So the parent reads less raw data, Python filters data locally, several jobs can run in parallel, while there can be an extra cost overhead as well. So every recursive child is another LLM. Duplicated investigations can waste tokens. Orchestration itself has model tools overhead. So while Prime reports lower token usage than native harness in some of its own evaluation because it can programmatically process data instead of repeatedly making the model read it, but there is no general guarantee that Prime is cheaper. A badly designed swarm can easily cost more than one focused codex session. Then when can Prime agent actually be used to its maximum capacity? So when we are working with long horizon tasks, the task runs for many turns, hours, and would otherwise compact repeatedly. So for example, large migrations, big monorepo audits, then for parallelizable investigations, the problem naturally separates into independent branches. So let's say if a parent can divide a bigger audit into smaller auth and API audits, now persistent subagents actually matter because the parent can continue talking to the same specialist instead of spawning disposable one-shot workers. Then for repeated learning. So if the agent is performing similar work again and can improve its own harness from previous failures and successes. And this is where slash refine, memory, skills, and reusable subagent definitions becomes useful. So the maximum value prime workload will sound something like keep working on this difficult objective for several hours, run many experiments, divide work among specialists, retain what happened, improve your workflow from failures, and only stop when a measurable quality gate passes. And that is where Prime's architecture stops looking like elaborate plumbing and starts making sense. The real question for Prime is therefore when the task becomes long enough that managing context, experiments, and other agents become part of the problem itself. Prime's programmable runtime manage that complexity better than ordinary context compaction or markdown or one shot subagents. And that is the claim worth testing.